Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So here we are on the second of two videos and what I find, well, a fun thing to do. Creating a band reject or notch filter using just coax. Now there are two ways to do this. The first and easiest method is using an open stub. This is what I showed you in the first video. Now I've put a link to this video up in the corner just for you in case you happen to miss it. The open stub method has the disadvantage of having somewhat higher emissions because it is an open stub. The second method is using a shorted stub. This has the advantage of lower emissions, but is definitely more difficult to implement. And this is what I'm going to show you in this video. As I said in the first video, these are definitely not narrow band filters. My bench experiments show that they have a Q of about 110, but could be a lot higher if you use two stubs and can get them tuned perfectly into coincidence with one another. There is some overlap of concept between the two methods, so if you've watched the first video, prepare for a little bit of review. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. The first thing I'm going to do is explain how this thing works. These filters do what they do because of the weirdnesses that are the realities of transmission line characteristics and the impedance transformations that occur as we travel down that same transmission line. Now, let's try to picture what's going on with these transmission line realities so we can understand how these filters work. Suppose I have a simple piece of coax and it has a dead short on one end. This means that the impedance at that end is some very low value. Now, let's track the impedance as we move down this piece of coax at a particular frequency. When we reach the place along this coax where the electrical length is 1/2 wavelength at the particular frequency in question, the impedance at that point is the same that we started with, a very low value, nearly a short. Now, suppose we were to install a T connector in the midst of a feed line and connect a very simple piece of coax to that T. The physical length of this coax is such that its electrical length is 1/2 wavelength at a particular frequency of interest. We completely short the other end of this simple coax. At the frequency at which this stub is 1/2 wavelength long, it will present nearly a short across the transmission line that it's attached to. Any signal traveling down that feed line at that frequency will be shorted out at the T by this coaxial stub. We now have a band reject filter at the frequency in question. Now my bench experiments show an attenuation around 30 to 40 dB doing just this. But you know, we can do even better than this. Suppose we want more than 30 to 40 dB of attenuation. How do we do that? Continuing with our transmission line impedance transformation realities, if we have a short at one end of our coax, then we will see a very high impedance at the far end of a 1/4 wavelength long piece of coax. With this in mind, let's think about it for a moment. The impedance at the T connector is low, nearly a short at the desired frequency. What if we inserted a piece of coax between this T and another T connector that was 1/4 wavelength long at the frequency in question? We're starting out with a very low impedance at the first T, and going through the impedance transformation of the 1/4 wavelength, we are presenting a high impedance at the next T. We now connect another shorted stub, which is 1/2 wavelength long at the frequency in question at this second T. Now, because it's a 1/2 wavelength long and it is shorted at the far end, it presents a very low impedance at the second T at the frequency in question. So we have a high impedance coming into this T, we have a low impedance at the T because of this stub, and with a voltage divider, high impedance in, low impedance out, we significantly reduce the voltage of the signal at this second T. And this is true here just as well. By adding this second T, I now have an attenuation of 70 plus dB at the frequency in question, assuming that we can perfectly tune these stubs to the same frequency. Now that we have an idea how it works, how do you design one of them? Designing one of these begins with knowing your materials, specifically the velocity factor of your coax that you're going to use. No matter what you do, you must know the velocity factor of your coax if you're going to do this. Now you can find this on the data sheet for a specific coax that you plan on using, or you can measure it for yourself using one of several methods. I outline these methods in my video series on the subject. I've put a link to the first video in the series up in the corner for you. Now, I recently added yet one more method of doing this, and I made a video on this. I've put that link up in the corner for you too. It is best if this velocity factor includes everything associated with your stubs. Your connectors, your adapters, your T's, everything. Well, the next step is to determine the specific frequency you want to notch out using this band reject filter. I'll call this F sub 0. The design all revolves around 1/2 wavelengths of coax. So our first step is to calculate what these lengths should be. To do this, we use the following formula. The physical length is equal to 0.5 times the speed of light times the velocity factor, all divided by the frequency in question, where the speed of light in free space needs to be in whatever units make sense for you. The units that you choose for the speed of light determine the units of the physical length that you calculate. I have provided the value for the speed of light in inches per second and centimeters per second in the description below for your convenience. Now, let's apply this to a real-world example. So here I am trying to work on the oft overlooked 1.25 meter band, which is 219 to 225 megahertz. And I am experiencing some significant interference from a very, very strong signal at 250 megahertz. I don't know where it's coming from. I just know that it is the culprit. So how do I get rid of it? Well, I'll create a filter using some coax with shorted stubs. Now, I have decided to use the datasheet value for the velocity factor of my coax for this project, which is 0.66. I will cut both of the stubs so that they coincide with the Miscreant 250 megahertz signal. So how long do our stubs need to be to make this work? Well, we will use this equation. The physical length is equal to 0.5, because that's the number of wavelengths long our coax needs to be, times the speed of light, times the velocity factor, which is 0.66, all divided by our frequency in question, which is 250. So stubs 1 and 2 with a frequency of 250 megahertz needs to be 15.58 inches or 39.5 centimeters long. Now the interconnecting coax is just half that because it's a quarter wavelength, and that comes out 7.79 inches or 19.79 centimeters. Now it is not possible to very, very precisely cut coax to an exact length. In addition to this, the velocity factor of our coax is not going to be exactly what the datasheet says it is, or even what we measured it to be. So I will cut my stubs a little long and then trim to tune. How much longer? Well, a good number for me is about 10% longer than calculated. This gives me a length of 17.14 inches or 43.53 centimeters. Now, to allow for the whole shorting thing, I will add the radius of the coax to these lengths. And in this case, because my coax is 0.25 inches in diameter, this is another 1/8 of an inch or 3.2 millimeters. I'll explain my method of shorting the ends when I get to the construction in just a little bit. So I will cut both stubs so that the entire assembly, including the B and C T, is about 17 1/4 inches or 43.815 centimeters. Now, the interconnecting coax isn't as critical, so I will cut and terminate it so that the overall assembly is the calculated length of 7.79 inches or 19.79 centimeters, including the B and C Ts, which will be installed at the ends. So let's go build this thing. So here is the complete assembly. Unlike the first video, I decided to terminate my coax in B and Cs and use the adapters for interconnecting things. Now, I did tell you that I'd show you how I did the shorts at the end of the stubs. So here it is. I stripped the outer sheath of the coax back the radius of the coax. In this case, my coax is 1/4 inch or 6.4 millimeters in diameter. So I stripped it back 1/8 inch or 3.2 millimeters of the outer sheath. I folded back the shield as far as I could, and then I stripped the center conductor of the coax as close to the shield as possible. I folded the shield back into contact with the center conductor of the coax, and then using some soldering paste, I soldered the shield to the center conductor. Now that we see the overall construction, let's see how it performs right out of the construction gate. Well, what are my expectations? My guess is that the frequency will be low, around 227 megahertz. So let's take a look. Well, the dip is right at 226.3 megahertz, only 700 kilohertz off of my expectations. Now we get to tune the thing. Well, how do we do that? So here you can see our starting place. We have one marker at my target frequency of 250 megahertz. The other marker is intended to track with the dip. To tune this filter, we have to trim off small amounts of length, and the higher frequency that the filter is tuned to, the smaller the amount that we have to trim. The real difference in trimming this to tune as compared to the open stub is that we have to solder the short at the end of the stub every time we trim some off. Here's one important note. The tuning of the stubs does affect each other. Once we approach this target frequency, we want to be sure to trim them both in concert with one another. Now, how much do we take off at a time? Well, I'm going to trim off a mere 1/4 inch or 6.4 millimeters and see how much of a change I see. Then, based on that observation, I will decide on how much to trim at a time. After having trimmed stub 1 to a little ways away from our target frequency, I begin to trim stub 2, then working back and forth between the two stubs to bring things as close to our target frequency as I can. I now have a single dip at 249.2 megahertz with an insertion loss of 62.3 dB. We are only 0.8 megahertz away from our target, and the difference in insertion loss between our target and where we're at is a mere 0.4 dB. Now, if we were able to perfectly trim these so that the two stub frequencies were perfectly matched, then we could get noticeably better attenuation at our target frequency. But trimming 1/8 inch is about the minimum we can trim, and this amounts to about 2 megahertz in change in tuned frequency. This 0.8 megahertz would be trimming somewhere around 52 thousandths of an inch or 1.3 millimeters. That just ain't happening. So I'm going to count this as good enough. But you know, one problem with shorted stubs is the length of the stubs. A half a wavelength can get pretty doggone long at lower frequencies. Wouldn't it be nice if we could do a better job of tuning and shorten the length of the stubs at the same time? And the answer to that question is, we can. But how? Suppose we were to replace our dead short at the end of the coax with some kind of inductor. Well, this fools the system into thinking that the coaxial cable is longer than it really is. The shorter the coax is, the larger the inductor you need to make it appear to be the length you need. But there is a limit to this. Your coax, including the effects of the inductor, needs to be a half wavelength long. Adding the inductor to the end of your coax can only make up a bit less than 1/4 wavelength. And in practical terms, this is right around 0.248 wavelengths. Inductance is a pretty tough thing to deal with because every wire is an inductor and their values changes with environment. From my bench experiments, it seems we would want to shoot for an inductive reactance around 100 to 200 ohms at the frequency in question. This will shorten the stub from a full 1/2 wavelength down to between 0.29 and 0.324 wavelengths and provides reasonable adjustability in whatever inductor you choose to use. If you choose to use an inductor with a larger inductive reactance, then it will require a larger change in inductance to affect a relatively small change in tuned frequency. While a toroidal inductor would work, it gives us no adjustability. On the other hand, if we use an air core coil, then we don't want to wind it close wound. This way we can squish the turns together to increase the inductance or spread them out to decrease the inductance for tuning purposes. This gives us some adjustability. The other option is to use an inductor which is designed to be variable like this one. It has a core that you can move in and out to change the inductance. But ones like you see here are clearly not intended for high power use like in a transmitter transmission feed line. So how do we go about designing one of these things? In order to design one of these things, we need to use a Smith chart. Don't let that scare you off. This process is actually a very simple application of a Smith chart. If you're interested in learning more about Smith charts, I'll point you to my video series on this subject. I've put a link to this first video in the series up in the corner for you. I've also put a link to a free downloadable Smith chart form in the description for you. With this said, remember that a Smith chart assumes ideal components. The feed lines are lossless, and the capacitors and inductors are ideal with no parasitic inductance or capacitance or resistance or any of that. The best we can do is plan for having to make adjustments to our design. Okay, back to the design itself. There are two ways that we can approach this design. In either event, you will need to know the velocity factor of your coax, the characteristic impedance of your coax, and the frequency of interest of the filter. All right, way one. You have a variable inductor like this little guy, and you want to know how long your coaxial stubs need to be to use your inductor. Way two, you already have prepared cables of a particular length, and you want to find out what inductance you need to make them work for your filter. So let's actually design a solution for these two scenarios using a shorted stub design. So here's the scenario. You live 5 blocks away from an FM broadcast station which transmits on 90.9 megahertz. And it is causing you some real issues. And you want to filter this frequency out. So for this demonstration, I know that my system is made up of some very, very old RG213U coax. According to the data sheet, the velocity factor of my coax is 0.66. The characteristic impedance is 50 ohms. The frequency of interest is 90.9 megahertz. But before I begin, let me give you one piece of very important advice. When you're doing this, be sure to build in enough variability into your design to accommodate variances in velocity factor, measurement lengths, connector and adapter velocity factor differences, and all of this stuff. Because there's a lot of, well, let's face it, RF magic going on here. So let's start with way one. With way one, we start with an inductor that we want to use and calculate the cable lengths we need to create to use it. My variable inductor varies from 200 to 400 nanohenries. So I'm going to design around 300 nanohenries halfway through its capabilities.
Step 1.
Our first step is to calculate the inductive reactance of the inductor at the target frequency. We have 300 nanohenries or 0.3 microhenries at 90.9 megahertz. This gives us an inductive reactance of 2 times pi times our frequency times our inductance, or 171.34 ohms.
Step 2.
The next thing we have to do is normalize the inductive reactance to the characteristic impedance of the coax that you're going to use for your stubs. To do this, we simply divide the inductive reactance by the characteristic impedance of the coax. So we get our 171.34, which we just calculated, divided by 50, which is the characteristic impedance of our coax, and we get 3.4268.
Step 3.
Now we get to pull out our Smith chart. Because we're talking inductance, we're going to be in the upper hemisphere. We look along the edge to find the normalized inductive reactance and place a dot on that spot.
Step 4.
Next, we draw a line from the center of the Smith chart out through the dot we just placed for the normalized inductive reactance, all the way to the outer edge of the Smith chart.
Step 5.
Our next step is to read the required electrical length off of the inner scale of the outer edge of the Smith chart where the line we just drew crosses it. According to my calibrated eyeball, I get 0.2948 wavelengths.
Step 6.
Now we get to calculate the physical length of the coaxial stub. This length will include the coax itself, any connectors or adapters which make up the entire stub assembly. This is a simple formula and one that we've seen many times before. The physical length is equal to the speed of light times the velocity factor times the electrical length, all divided by the frequency in question, where the units of the speed of light must be the same as the desired units to be used in measuring the stub assembly. I've placed the value of the speed of light in mega inches per second and mega centimeters per second in the description for you. In this case, the length of our stub assembly, including the T, the connectors, the coax, right out to the place where the inductor is soldered to our terminating connector, is 25.26 inches or 64.16 centimeters. Well, looky here. My cables just so happen to be already just the right length. Go figure. So let's go on to way 2. Well, I dug around in my old cable box and found some cables that seemed to be long enough, but not too long. They need to be between 1/4 and 1/2 wavelengths long at the desired frequency. The frequency in question is 90.9 megahertz. The velocity factor of my coax is 0.66. So that means we calculate the appropriate length equals the speed of light in free space times the velocity factor times 0.25 divided by the frequency in question, which gives us 21.42 inches or 54.4 centimeters, for 1/4 wavelength, and twice that, or 42.84 inches, or 108.8 centimeters for the half wavelength. And these cables that I found are 25.25 inches, or 64.135 centimeters long, including the T at one end and the terminating end connector that the inductor is soldered to at the other. So these will do the job just fine. So let's get started.
Step 1.
Our first step is to determine the electrical length of our cables at the frequency in question. To do this, we use the following formula. The electrical length of the cable is equal to the physical length times the frequency in question, all divided by the speed of light times the velocity factor. So we have 25.25 times our frequency, which is 90.9 megahertz, all divided by 11,802.85 times 0.66. And according to this calculation, our cables, including all of the adapters and the connectors, are 0.295 wavelengths long.
Step 2.
Now we get to break out the Smith chart. Now, looking along the edge of the Smith chart, on the inner scale of the outer edge, we find our electrical length of 0.295 wavelengths, and we put a dot there.
Step 3.
Our next step is to draw a line from the center of the Smith chart out through the dot that we just placed on the electrical length.
Step 4.
Now we move to the outer edge of the inner part of the Smith chart and read the value of the normalized inductive reactance. I used my calibrated eyeball and I see 3.45.
Step 5.
Our next step is to unnormalize the value we just read from the Smith chart. We do this by simply multiplying the normalized value by the characteristic impedance of the coax, or 50 ohms in this case. So we get 3.45 times 50, which gives us 172.5 ohms.
Step 6.
And so now we come to our last step. We calculate the required inductance from the inductive reactance and the target frequency. The inductance is equal to the inductive reactance, all divided by 2 times pi times the frequency. That gives us 0.302 microhenries, or 302 nanohenries. Well, oh my, isn't that just a coincidence that the inductor that I want to use just happens to be 300 nanohenries? Let's put this thing together and see if our calculations actually work. So, here is the complete assembly. I set the inductors so that their inductive reactance is somewhere close to the 172 ohms at 90.9 megahertz. So how does it look right out of the assembly gate? We have two little dips here, one at 95.22 megahertz and one at 96.64 megahertz. So let's tune this down to our 90.9 megahertz, which is what we want. There we go, stub 1. All right, and now we do stub 2. Now these are going to interact just a little bit, so you kind of have to go back and forth between the two of them to get it right. And when you get it exactly dead on, you can get some pretty impressive rejection numbers. So there we go, that's pretty doggone good. We have at 90.9 megahertz, we have an attenuation of 86 dB. I would call that a success. Well, now you have the long and the short of it all, pun intended. You can do this thing. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-oots.